Okay, so we said the change in entropy for the universe is equal to the change in entropy for the system plus the change in entropy for the surroundings. The change in entropy for the surroundings is equal to negative delta H for the system divided by T. This is at constant pressure and temperature. So if we multiply all of this by negative T, well, first of all, let's combine the two reactions. Delta S for the universe would equal delta S for the system plus negative delta H for the system divided by T. See what I did there? I took this and put it in for that. Now we're going to multiply this by negative T. So we're going to get negative T delta S for the universe is equal to negative T delta S for the system plus negative T times negative delta H for the system over T. So these T's are going to cancel out, and those negatives are going to get rid of each other. And so what we can do, because this is kind of awkward, I'm just going to rearrange those. Everybody okay with that? So we're going to stop using the cis subscript. And we're just going to assume that if there's no subscript, we're talking about the system. If we're talking about the universe, we're going to write universe as the subscript. Okay? So negative T, change in entropy for the universe, is equal to delta H minus the temperature times the change in entropy for the system. So here's another quantity. You know, we had enthalpy and entropy, and now we've got Gibbs free energy. So Gibbs free energy is defined as H minus Ts. So H is the enthalpy, T is the temperature, and in kelvins, and S is the entropy. So the change in Gibbs free energy, delta G, is going to equal delta H minus T delta S. So the change in Gibbs free energy for a process occurring at constant temperature and pressure will be proportional to the negative of the change in energy for the universe. So Gibbs free energy is also a criteria for spontaneity. It's sometimes called chemical potential. It's like mechanical potential energy, right? We're always going to lower potential energy. Things fall down, they don't fall up. Gibbs free energy spontaneously is going to change in a negative direction. So chemical systems tend towards lower Gibbs free energy, just like they tend toward lower mechanical potential energy. So if delta G is negative, then you have a spontaneous process. So we can calculate delta G looking just at the system. Because what did we just say delta G was? Delta G is delta H minus T delta S. This is the change in entropy for the the system. This is for the system. And so we can calculate delta G without having to consider the entire universe. So we need to know what delta H is. We learned how to do that back in chapter 7. We need to know what delta S is. We just covered that. And here we have a graph showing Gibbs free energy and how it determines the direction of spontaneous change. So here we have higher Gibbs free energy, lower Gibbs free energy, and this would be the reaction progress, going from reactants to products. And we learned that the reaction quotient can help us to predict which direction a reaction is going to go in. Because this is an equilibrium, right? It's going to come to an equilibrium at some point where there's going to be no net change. And that's going to be where Q is equal to K. Where Q equals K, then we have equilibrium. Over here, if Q is less than K, it's going to go forward. So that tells us that delta G is becoming more negative. Here, we're not going to have a spontaneous reaction going this way. It's going to come the other way. Does that make any sense at all? So this is a little bit like, looking at land. Here's a hill and it comes down. There's a valley down here and it goes back up. And you're thinking about where's the ball going to go? If I stick a ball right here, it's going to roll down here. It might roll up a little bit. It's going to settle down here at the lowest mechanical potential energy. The reaction is going to settle at the lowest Gibbs free energy, the chemical potential energy. And so we can look at which direction, what's spontaneous is that going to cause a negative change in G? Then it's going to be spontaneous. Going this way would cause a positive change in G that's not going to be spontaneous. So all three of these things, delta S, delta H, and T, have an effect on spontaneity. So we'll look at different combinations. You got negative delta H and positive delta S. So this would be an exothermic reaction with a positive change in entropy. So for this one, the reaction is going to be spontaneous at any temperature. Delta H was negative, delta S is positive. But we're taking a negative number and we're subtracting a positive number. That's just going to become more negative, right? It doesn't matter how big or small T is, this is going to end up a negative number. Negative delta G, spontaneous. So I personally have a problem because a change in S that's positive is associated with being spontaneous. But here, delta G being negative is spontaneous. So kind of the way I think about this is delta G is going to behave a lot like delta H in its positive-negative business. Delta S, entropy. Entropy is weird. It goes the other way. And so that's how I remember. An example here, we've got 2 moles of gas going to 3 moles of gas. So the change in entropy here is positive. So delta S is positive, delta H is negative. So when we combine those, we're going to get negative delta G. This is going to be spontaneous at all temperatures. Any questions? What if we have sort of the opposite? Delta H is positive, delta S is negative. So now we have a positive here, and we're subtracting a negative. Well, that's going to make delta G positive. Doesn't matter what the temperature is, it's always going to be positive. So this is going to be non-spontaneous at all temperatures. And if I remember, there are questions like this in the exam bank, the test bank, where, you're given this on the sheet of useful information. It's not going to be given in the question. But they'll talk about things like, well, delta H is this, or, give you some information where you can figure out the sign of delta S, and they're going to ask you, like, at what temperature is this spontaneous? Or, is this spontaneous at all temperatures? They'll ask you questions about that, where you're not necessarily doing a calculation. You're just predicting whether delta G is positive or negative. And we're doing that based on looking at the signs of these. If this is positive and that's negative, then this will always be positive. And you don't need to remember that. You can just think it through. Well, delta H is positive. This is negative. Oh, I've got negative times a negative 1. That's going to mean this is going to be positive also, overall. Positive and positive, delta G has no choice. It has to be positive. And then we get the one where we have both delta H and delta S being negative. So we've got exothermic reaction. Change in entropy for the system is negative. This is going to depend on the temperature. Here we've got, this is negative. This is also negative. If we're subtracting a negative, that's adding, right? So it depends on how big T is. If T is big, then this term is going to be larger, and we could have this be positive. If T is small, and we're adding a small amount to this negative number, delta G is going to be negative. So it will be negative at low temperatures and positive at high temperatures. So this is something that's spontaneous at higher temperatures. I'm sorry. See, there I go with the backwards again. Negative delta G is spontaneous. I'm like, wait a minute, this isn't working. Okay. I never said that wasn't confusing. In fact, I'm just going to tell you, it's very confusing. Delta S is the only one that wants to be positive. So negative at low temperatures. Let's look at this. We've got liquid water going to solid water. That's freezing, right? Is freezing spontaneous at high temperatures or low temperatures? At low temperatures, right? Now, here, is the entropy increasing or decreasing for this system? It's decreasing, right? It's becoming more ordered. And that's fighting against, right, spontaneity. But delta H is negative. And so that overpowers it, and overall, delta G is negative. And then we've got both of them being positive, and this is going to be the opposite situation. Positive at low temperatures, negative at high temperatures. So here, water going from liquid to a gas, evaporating or boiling, that's going to be spontaneous at high temperature, right? Delta S is increasing because we're going from a liquid to a gas. Delta H is positive. And so if this is large enough, if the temperature is large enough, this whole thing can be negative. That's just a lot to think about. If delta H and delta S have the same sign, the spontaneity depends on the temperature. And you can find the temperature at which the spontaneity changes by saying, well, that would be at 0. That's where it's neither positive nor negative. So we can put in delta G as 0, and we can figure out what that temperature is. This is a table summarizing the previous few slides. I just really don't think it's all that useful. So this is asking us to calculate delta G at 25 degrees Celsius and determine whether the reaction is spontaneous. So this is a sort of a calculation that you might find on an exam question. Delta G is delta H minus T delta S. So they're giving us delta H, they're giving us delta S. I mean, we could look at this and say, oh, it's going from 2 moles of gas to 1. The change in entropy should be negative, but we don't know how much negative, right? So they're telling us how much negative. And here again, we got to watch out for this kilo business, right? This is kilojoules, that's joules. It's going to be that way, and so we just have to deal with it. So we're supposed to calculate delta G. Well, let's put in delta H. Minus the temperature, got to put this in Kelvin, 298 Kelvin. And the unit on delta S should help you remember that. And then we're going to put in our delta S minus 120.5, joules per Kelvin. So the kelvins cancel out, but we're going to have kilojoules minus joules, or plus joules. You can put it into joules, you can put it into kilojoules. You have to pick one. Well, I think it's easiest to just change this by going times 10 to the 3 and just have it be joules. Negative 137.5 EE3 minus negative 120.5. So is joule the best unit for that quantity? No, it's not. But that is an answer. Pretty sure they're given the answer in kilojoules. Okay. Yes, I made a boo-boo. It's like, wait a minute. I forgot to multiply by 298. Well, that wouldn't change anything, would it? Oh my goodness, yes. Okay, let's try that again. There we go. So in kilojoules, that would be minus 101.6 kilojoules. Okay? Don't forget to multiply by the temperature. So, is it spontaneous? Yes, delta G is negative. S is the one that wants to be positive. So then it's asking, is delta G going to become more negative or more positive as we increase the temperature? It's going to be more positive because these minuses cancel each other out, and so then we're adding here. The bigger this is, the more positive delta G gets. If delta G is more positive, is that more or less spontaneous? Less spontaneous. Not confusing at all. Is it spontaneous? Yes, it is. Delta G gets more positive as T increases. And, that can be kind of hard to think about it. There's people who like conceptual stuff. It's like, leave the numbers out of this. And then there's a bunch of us that could we just do an actual calculation instead of thinking about this? Well, what do you do then? Well, stick a number in that's bigger than 298. Maybe 1,000, right? See what it does. There's your answer. So if delta G becomes more positive at some point as you're increasing the temperature, it's going to go from negative to positive and not be spontaneous anymore. Any questions?